All right, welcome back to chapter 16. We're going to dive a little bit deeper into acids and bases and define them based on what they do in solution. Okay. There's multiple different definitions of acids and bases. All of these definitions are valid definitions. Some of the first ones just have a few limitations. So as scientists found the limitation of that definition, they had to come up with a more inclusive definition. So each of these kind of builds on one another. If it's an Arrhenius acid, it's also going to be a Lewis acid. Nothing changes. It just gets more inclusive. So we've got our Arrhenius definition, our Bronsted-Lowry definition, and our Lewis definition. So here's just a nice kind of preview or review of each of the definitions. I'm about to dive into each one, but I like to offer this up front so that you have something to go back to and reflect on once you've learned them. So the Arrhenius definition is defines acids and bases with respect to aqueous solutions. So another way of saying that is, well, what happens when I put an acid into water? What happens when I put a base into water? Okay. So first we have an acid. So when we put an acid into water, it's going to produce or increase the number of hydrogen ions. So we'd have HCl, no ions before we put it in water. So we got a beaker up here of just pure HCl. We dump it. We dump it into water, and those two ions will dissociate or break apart. And what will they break apart into? Will they break apart into hydrogen ions and chlorine ions? The presence of the hydrogen ion is what defines this as an acid. So it increases the number of hydrogen ions in that beaker. So that's how we define it as an Arrhenius acid. Bases produce the hydroxide ion. So our poster child for base is sodium hydroxide. So before we put it into water, it's just NaOH, nothing, no ions, just pure NaOH. When we put that into solution, it's going to break apart into sodium ions, and it's going to break apart into hydroxide ions. The presence or the increase in hydroxide ions is what defines this as a base. Okay. One of the things that I like to point out here, because a lot of chemistry textbooks don't do a good job of explaining this, but they use it throughout the chapter. So I want to just break this down really quick. So remember that all of this is happening in the presence of water, right? So all of these ions are floating around in H2O. Those hydrogen ions are really, really unstable. So if you think about a hydrogen ion, right? So let's think about a neutral atom of hydrogen, right? So neutral hydrogen has one proton and one electron, correct? When it becomes a positively charged ion, how does that happen? How does something become positively charged? Well, it gives away or somebody steals his electron. So if we look at an ion of hydrogen, it's just a proton floating around, right? Well, you can imagine that that would be pretty unstable for just a proton to be floating around. So if hydrogen is floating around in the presence of water, what it's going to do is this hydrogen ion is going to see this molecule of water and say, hey, I can latch on to that molecule of water and I can gain a little bit of stability. Okay. So what does that look like? So we've got this hydrogen floating around. It's in the presence of water. If it latches on to this molecule of water, it becomes this molecule right here. So H3O. This molecule right here is called the hydronium ion. So hydronium Hydronium ion. When these hydrogen ions are in the presence of water, they will automatically form this hydronium ion. So very often chemists will use H plus and H3O plus synonymously. They'll go back and forth. You'll see both in the problems or one in the problems. So they use these synonymously. They really do basically mean the same thing. If this guy is in the presence of water, he will automatically become that guy. But I like to just really lay that out on paper for you guys, because you start to train your eye to see one thing, and then all of a sudden the textbook throws in the other, and you're like, whoa, where did that come from? So just a little helpful hint here. Okay. The other thing we want to talk about here is just remind ourselves what is going to dissociate or break apart. How do we know? That sort of thing. So back in Gen Chem 1, we talked about something called an electrolyte. So remember, an electrolyte is an ionic compound that will break apart or dissociate when we put it into solution, right? So we've got a non-electrolyte, a weak electrolyte, and a strong electrolyte. So let's just remind ourselves what those are, because acids and bases do mirror these things a little bit. So a strong electrolyte is going to be something that completely dissociates in water. So our poster child for strong electrolyte was sodium chloride. So every molecule of sodium chloride that I put into water will break apart into sodium ions and chlorine ions. Okay, every single particle will break apart. We see that one-sided arrow. All of it's going to go to the dissociated side. A non-electrolyte does not form ions in water. So our example of this would have been sucrose or sugar. So sucrose is this big molecule with a bunch of carbons and hydrogens and oxygens. And when I put sucrose into a beaker of water, it stays together as that one big molecule. It does not break apart or form any ions. It just stays together. And then we have this kind of gray area in the middle. So our weak electrolytes will dissociate, but they will partially dissociate in water. And what we're going to see with weak electrolytes and ultimately weak acids and bases is they form an equilibrium. So this is where I said those ice tables are not going away. So acetic acid is actually, let me write this correctly, C3. Acetic acid is actually an example of a weak acid or a weak base. I did this all dyslexic, hang on. C2H3O2, there we go. So acetic acid is an example of a weak electrolyte, also a weak acid. So when it dissociates, some of it breaks apart into hydrogen ions and acetate ions, but some of it stays together as this molecule. So we're going to see this two-sided arrow, this equilibrium, dynamic equilibrium that forms, and we'll get to use our equilibrium skills again. Okay, so just something to think about. How do we know if it's going to break apart in solution? Well, it's either going to be a non-electrolyte, it won't break apart. A strong electrolyte, it completely breaks apart, or a weak electrolyte, it only dissociates partially. Okay, so we're going to take these ideas, and instead of saying electrolyte, we're going to use the word acid and base for strong and weak. Okay. So let's first look at strong. So a strong acid or a strong base is going to dissociate or ionize. This is another word for dissociate. or break apart into its ions. So ionizes break apart into its ions. So a strong acid or strong base is going to completely ionize. So what we see here is this one-sided arrow. Every single molecule of this acid is going to break apart into hydrogen ions, and then we use this generic A for whatever it was attached to, that anion. Okay, so single-sided arrow, strong acid, strong base. Okay. For a weak acid or a weak base, we're going to see this double-sided arrow. We're going to see this equilibrium. So some of the acid breaks apart into its hydrogen ions, and then whatever it's attached to is anion. Some of it stays together as this complex, as this H attached to the anion, okay? And we will see an equilibrium, dynamic equilibrium take place here, okay? So as our introduction to acids and bases, so far we've looked at the Arrhenius definition. So Arrhenius definition has to do with an acid or a base when we put it into water, when we put it in an aqueous solution. But before I leave you for the next video, I want you to think about what may be one of the limitations of the Arrhenius definition. Yeah, what if we're not dealing with an aqueous solution? What if we're dealing with something else? Okay, we'll talk about the Bronsted-Lowry definition in the next video. I hope you guys found this helpful.